me first pay the person operating the camera. Whoa! Okay, so first of all, over the last few days, I decided to update the numbers in the chapter on general relativity using the latest data published by the Planck collaboration. And there are small changes, and I just thought I'd tell you what they are. I'm putting them in the new update of the book, but let me just give you the basic changes are that the era of radiation seems to have ended essentially at 51,956 years after the Big Bang. Now, not all those digits are significant. Let me give you the my estimate of the error bars. They're pretty small. It's a plus or minus 353 years. So that's when the era of radiation ended. The present Hubble rate, by the way, 0 means now, is 67.74 plus or minus 0.46 kilometers per second per megaparsec. I don't even know what the abbreviation is for megaparsec. Oh, I got it right by accident. Okay. This is, I think, the right name to call this, since it's inverse time. It's really a frequency or a rate, so I'm calling it the Hubble rate, and not the Hubble constant, since in one case it's not constant, since it's not constant for one thing. And moreover, the thing that's really important is T0, or the Hubble time. I should call it, well, I don't know what to call it. Anyway, the Hubble time is 1/80, and this is 14.76 plus or minus 0.1 giga-years. The critical density, rho c, which of course is defined as the density that gives you a perfectly flat universe, is 8.6194 times 10 to the minus 27, and I decided to use actual MKS units, kilograms per meter cubed. So that's the critical density. The ratio omega omega. Well, let me first say what omega lambda is. Omega lambda is the ratio of the energy density, of the dark energy density, or dark mass density if you want, to the critical density. And the latest version of that omega lambda is 0.6911 plus or minus 0.0062. The fraction due to matter, which is omega matter, this is the matter density divided by the critical density. This is 0.3089, and it has the same errors, 0.0062. I hope that's not a typo. I think I should check the published version. These figures are from the archive. The archive uses the LaTeX from the scientists and the software of the archive, so the pictures and the equations turn out to be correct. On the other hand, typos may be caught in the published version or created in the published version. The published version, because it's published in an astronomy journal, they don't have very good software and they screw things up. I assume none of you are going into astronomy.
No.
I just can't resist criticizing astronomers. The total omega is the total density of the universe to the critical density, and this is the present version of that. This is 1.0000 plus or minus 0.0088. So that's so that means that the constraint, the evidence for inflation is even tighter than what it was due to the 2013 release of the Planck data, which was in turn even tighter than the WMAP data, which was earlier. The age of the universe, I guess I'll just call it age, is 13.799 plus or minus 0.021, again, bigger years. Okay, did I leave anything out? All right, I think that's basically the main thing. I think I'll just content myself now with just giving you the facts. So any questions? All right. So we were talking about cosmology, and I think basically we had basically finished the GR and the cosmology. The only thing, maybe I should just give sort of a wrap up for what actually seems to have happened. So I'll just mention these data again. So first there was inflation. Again, this is, I'm assuming that there was inflation. There's evidence for it, but it's more circumstantial than direct. I don't think I could get past Justice Roberts. Also, in calculating these things, I assumed that that this omega lambda, that is to say that the dark energy density, I've assumed that the dark energy density has always been the same, and that it's just the energy of the vacuum. Now, nobody knows what dark energy is. It could be something else. And in fact, it's even conceivable that, it's even conceivable, I suppose, that there was a field which people call by the ugly name the inflaton, which I think is just awful. It's a combination of English with Greek, which doesn't always lead to good offspring. Anyway, I don't know why I said that. Probably better to mix the races as much as possible. Anyway, not that Greeks and English are any different races, but anyway, where the hell was I?
Inflotron.
Oh yes, all right. So what seems to be true is that inflation was caused by one or more scalar fields, assuming for some reason, possibly just a quantum fluctuation, a high value momentarily in at least some tiny region of space-time. And then led, just by ordinary classical general relativity, to an enormously rapid expansion of that region, and led then to a macroscopic, within a fraction of a nanosecond, and probably a very tiny fraction of a nanosecond, led to something macroscopic that was totally homogeneous, and there were the same potential energy everywhere because it came from the same fluctuation. So the same potential energy everywhere apart from quantum fluctuations. This potential energy then turned into radiation, and that was the Big Bang. Okay, so that's the very early thing. Then there was an era of radiation, which, as you see here, is essentially 52,000 years. Then there was an era of matter, which, did I write down the, oh, I forgot to give you the main, I left out the main things that I computed with considerable effort. The era of matter, well, I said when the era of radiation ended, which is approximately 52,000. The era of matter ended at 10.427 plus or minus 0.07 gigayears. And since then, and that is 3.372 gigayears ago. And since then, we've been in an era of dark energy. Now, when I say this was an era of radiation, what I mean is that the energy density of the universe was mostly due to radiation. Here, the energy density was mostly due to matter. Now, it's mostly due to dark energy. But mostly means, you know, like 69% as opposed to 31%. And something else that I forgot to mention is that the baryon fraction, omega baryon, is 0.0486 plus or minus 0.00720. So that's 15.7%. So 15.7% of matter is baryons. And of course, there are a similar number of leptons, but the leptons are at least 2,000 times lighter, so they don't really count. Okay, so that's that I think is enough of that. Now, shall I review Yang-Mills theory briefly, or have you heard that from me so many times that you wake up at night dreaming about it?
I dream about it.
Yeah, I'm okay for you. Skip it.
You want?
I'm okay for you. Don't cover it again.
If I do cover it or don't?
Don't.
Skip it?
Yes.
All right. Okay. All right. If we skip that, then I'll just skip the rest of this chapter. And in fact, I see that, well, and so now I'll go to string theory, but I mean, I must tell you that I have not worked on string theory enough to really feel comfortable with the subject. So I'll be just giving you a version that's a little bit better. At least today I'll give you a version that's a little better than what's in the book, because I've improved that a little bit. But if you're still interested, I will try to do things in more detail next week. But I mean, you know, if instead you'd rather that I do probability or something else, we can. But you got to tell me at the end of the lecture or by email in the next couple of days. Okay, because I only heard that you guys wanted string theory a couple of hours ago in the email. Of course, I should have asked you last Wednesday, and it didn't occur to me. Planning is not something I do well. Okay, well, what is this business with the string? The basic idea is that you have a string whose coordinates are x mu, and they're often written as capital X mu, and they depend upon where you are on the string, which is sigma, and tau, which is, I guess, a proper time of the string. Okay. Or we can just, at least at the level of precision that I'm using today, we can just think of it as casually as time. And okay, so what's the action? Well, Nambu and Goto introduced an action which is minus T0 over C, an integral from an initial time to a final time, d tau, an integral along the string from 0 to sigma 1, which is the, let us say, length of the string. And then it's a square root, and it's a dot product of the time derivative, or the tau derivative, dotted into the sigma derivative squared minus the time derivative squared times the space derivative squared. Okay, so that's the action. What is this action? Well, it's basically the area swept out by the string. And the reason it has a complicated form is so that if you change the parametrization of sigma and tau in an arbitrary way, the action remains invariant. So it's said to be reparametrization invariant, which is an awfully long reparametrization invariant. I may have spelled parametrization wrong. Okay, what is this dot product here? Well, the dot product here is that we're using a metric minus 1, 1, 1, 1, 1, 1, however many mu's there happen to be. And it's funny, we think of these, people have thought of these mu's as space dimensions, and then the issue of how many of them became a critical issue for many people. On the other hand, you know, these, you can think of these as just, so to speak, string fields, and I don't know, I'm not nearly as bothered by the extra dimensions as I was, say, 30 years ago. And part of the reason is that the easiest way to think about general relativity is to say that you have some space-time manifold that's curved. It's a four-dimensional manifold that's curved in some extended space-time, and that, to me, that looks a lot more, it's a lot easier to imagine that than to just say that, well, we have a four-dimensional curved space-time, and we're not going to say anything about what that means. The geometers back 100 or 150 years ago were very happy when they realized that they could describe the curvature of any manifold just by measurements done in the manifold. That's called the intrinsic curvature. On the other hand, the intrinsic curvature is the same as the external curvature that you measure if you put it, if you embedded it in the higher space. So, I don't know, I'm not, I mean, it's true that that was a great mathematical achievement, but whether there are extra dimensions either to incorporate the curve spacetime or to incorporate string theory isn't something that particularly bothers me. It used to bother me a lot. It doesn't bother me at all now. On the other hand, when you get older, you just sort of, what the hell? But, okay, so in other words, x dot x prime is just basically x dot mu eta mu nu x prime nu. And where eta is this metric here, which has one time dimension with a minus sign and as many space dimensions as you need. Okay. All right, so that's that. Now let's since this is reparametrization invariant, let's use a very simple parametrization. Let's just say that tau is time and sigma is length along the string. And so what is x dot d tau? Well, that's just going to be dt, because all the x dot will have many coordinates, and I'm using c for 1. Well, actually, c pops in and out of the equations. In this equation, c is probably 1. And then x prime d sigma is some d length, and I called it dr here. So then what we have is x dot x prime is actually 0, because this thing only has a this is a time derivative, and this is a d sigma derivative, and actually it was always clear to me why this thing was okay. Here we're just talking about a string that isn't doing anything, so it's just sitting there. That's why x dot d tau is just dt, and x dot d sigma is the length. That is to say, the word line of the string is just sitting there, and it's just moving forward in time like this. So there's no, the space coordinates, actually they would be changing in time, wouldn't they? Right. So this would be, this x dot would seem to be something like 1 comma v, where v is whatever the velocity is. Oh, no, I'm sorry. The thing is, the thing is lying there. It's just going forward in time. So this is all 0. So in other words, the space coordinates of the string is just lying there on the floor. Okay? So the time components change as it gets older. But the space coordinates do not change. So this looks like that. And this part is just basically 0, and what would that be? That would be whatever coordinate was maybe over here. It might be a 1 back there. In any case, the dot product is 0. So in that case, if we look at this action here, swing the camera around a little bit. This term vanishes for the string that's not doing anything. This term vanishes. We just have this. This then is is basically 1, and what we get then is that that's 0, and minus x dot squared d tau squared is just dt squared, and x prime squared, d sigma squared is just dr squared. And so this whole action here turns out to be something very simple. It's just, in this case, it's minus t0 over c, integral d, dt dr, and that's just minus t0 over c, t final minus t initial times, I guess, sigma 1, which is the length of the string. And so that is the area that the string sweeps out, because the string here, swing around here maybe, the area here is the string is just lying there, and it sweeps out this area in time. Length sigma 1, and time is going like that. Okay, so that's that picture. Now, let's now consider the thing much more generally, and consider what the equations of motion might be. Well, first of all, the variation of x dot mu is the time derivative of the variation of x mu, and similarly, the variation of x prime mu is the partial with respect to the length along the string, sigma of the change in x mu. So these are the things that we've done many, many times when talking about the principle of least action. Okay, so now the Lagrange density is minus t0 over c times the square root of x dot x prime squared minus x dot squared x prime squared. So that's the Lagrangian. And the change in the action is an integral d tau integral d sigma, so 0 to sigma 1, ti to t, tau I to tau f, of partial L partial x dot mu, and the change in x dot mu is d by d tau of the variation of x mu. So with this big chalk, this is going to take up a lot of space. Partial L partial x prime mu partial sigma of the variation of x mu. All of that d tau d. Well, I already have the d tau d sigma, so I don't need to do that. Okay, so now these things have special names, and unfortunately they're rather complicated. P tau mu is partial of L with respect to x dot mu, and P sigma mu is partial L partial x prime mu. Okay, so these are the two things that occur here, and because the action density is complicated, this is a little bit complicated. So P tau mu, which is partial L partial x dot mu, and notice that this is very much like ordinary mechanics. The momentum is the derivative of the Lagrange density with respect to the time derivative of the field, and so we consider each of these x mu's as fields of some sort. They're fields of a two-dimensional field theory, and field theory in two dimensions is a lot simpler than field theory in four dimensions. So that's one of the reasons why string theory has been so popular with theorists, because it's quantum field theory in two dimensions. There's a hell of a lot that you can do in two dimensions you can't do in four dimensions, and so people have people have liked this theory. Anyway, what is this thing? It's minus T0 over C, and then it's rather complicated. It's x dot x prime times x prime mu minus x prime squared x dot mu, and all this over this, what's essentially the action, namely, or the action density, mainly x dot x prime squared minus x dot squared x prime squared. Okay, so that's one. The other one is p sigma mu, which is partial L partial x prime mu, and this is a similar expression. So I'll just write over the same square root, but what's up here is x dot x prime times x dot mu minus x prime squared x prime mu. And I think there's a typo here. I think this should be x dot squared. Okay, so that's evidently when you differentiate with respect to x prime mu, this term over here, you get an x dot squared and then an x prime mu. Okay. So the change in the action then is integral d tau, integral d sigma, and it's this is after integrating by parts. So in other words, so maybe we should swing around the thing over here. So in other words, we integrate by parts with d by d tau, d by d sigma, and then we have the surface terms. Okay. So the when we integrate by, or rather the surface terms are these, namely, wait a second, now I've got myself confused. Hold on a second. Right. Oh, I'm sorry. When you integrate by parts, of course, you don't just flip this thing backwards. You have these extra terms. So I don't know why I'm taking so long with this. So this is what we get. So I'm sort of doing integration by parts by hand. That's why. Okay. All right, so this is the whole 9 yards. This is the simple term from integration by parts that we know, and this is normally the only thing we keep. And I could have written this as p tau mu dot and p sigma mu prime. That would have been a more economical notation. In any event, what we get is we get the equations of motion then. P tau, if I do use some more economical notation, it's p tau mu dot plus p sigma mu prime equals 0. So these are the equations of motion of the string. On the other hand, we've got these two terms to deal with. Now this term is the one we normally blow away because we say, well, we're interested in finding the equations of motion for the case in which the process has the least action going from an initial configuration to a final configuration, so we don't vary the initial or the final configuration. And so when we do that partial integration detour, we have the change in x mu at the final and initial points. They're both zero. So this one we forget about. But we have another term, and in order to have that term be zero, we need not only the equation of motion, but we need an integral of this thing, which is to say, an integral over time, d tau, from tau I to tau f. I should have put in the limits here. Of this thing, which is variation x mu, p sigma mu. So this has to vanish also. And this is something new to strings that doesn't occur normally in mechanics. At least I've never seen it in mechanics. And so now, oh, I'm sorry. We do. I left out something. This is it's the integral d sigma. So it's this at sigma 1 and 0. It's the space, the integral along the string of this at the two different times that has to vanish. So I'm sorry, the time integral of the difference. Okay. Now, there's one case where, bingo, no problem. Namely, if the string is closed. So you have a closed string. Then, as you integrate around here, this thing for sigma equals 0 and this thing for sigma equal to sigma 1, it's exactly the same object. We're talking about 0. So for closed strings, this vanishes. For open strings, we've got some choices to make. And one is we can say that p mu, p sigma mu, at all times, and at sigma star, meaning the initial and final positions, we can say that that just simply vanishes. And these are called the free endpoint boundary conditions. The other is the Dirichlet boundary condition, where we can say, well, at the ends of the string, there's no motion. In other words, the ends of the string are stuck somewhere. And so that is the change in x mu at any time, sigma star, is 0. And these are called Dirichlet boundary conditions. And for some time, these were very mysterious. Obviously, if you were doing closed string theory, you don't need to worry about this stuff. But if you're doing open string theory, then you either have to choose this or that, and this was puzzling. And then I think it was a guy at Santa Barbara who used to be at the University of Texas came here and gave a very nice colloquium. I think we actually all played basketball. But what is his name? I don't remember. Tall, good-looking guy. He wrote 2 books called On String Theory. No. Anyway, what he realized was that what was going on here could well be that you have some surface and the string is kind of attached to these 2 ends. And so because it's attached there, delta sigma is 0 at all times. Those things never move. Okay. And subsequently, these things are called D-branes. And they should be called P-branes because I think the guy's name began with a P. Terrible names. In any event, of course, they didn't want to call them P-branes because that's a slang term. Now, for the time component, you have to use the free endpoint condition because clearly the time component changes because even though the string doesn't move on the D brane, it gets older. And so the zero component changes. So delta x0 is not 0, so you have to use p sigma 0. So this is always true. In other words, p for open strings, p0 sigma or sigma star equals 0 is always enforced. You can't get away from that. And so a nice picture of open strings then is this plus that. And some people think of this brane on which they're attached, that's four-dimensional space-time. Or maybe three-dimensional space. And so that means then that the strings venture out only in a limited way into the extra dimensions. And the reason why, by the way, these strings in this picture, they're infinitely thin, but they're also short. And they're short, why? Well, because the energy of the string is the energy of the string, of course, is whatever the action is apart from the time. And so all this is the energy of the string. That's the integral then d sigma of the length. The integral d sigma of the square root and then times these factors. And in fact, the actual arcs, let's swing over here. The energy of the string then is T0 over C times the length of the string. So this being the time, and action is energy times time. So T0 is the tension in the string. Okay, so we've got a little more time here to do two things that are simple. First of all, this p tau mu is essentially a momentum density. And the angular momentum of the string is essentially an integral 0 to sigma 1, or let's say it's proportional to x1 p2 tau minus x2 p1 tau. So this is the normal expression for angular momentum. It's r cross p. So it's like so the angular momentum in the three direction then is x1 p2 minus x2 p1. And we can choose a simple parametrization where x, we're just looking at we'll just take two components of the string to be non-zero. Think of them as x and y. And I've chosen the sigma 1 over pi cosine of pi sigma over sigma 1 times cosine of pi ct over sigma 1 comma sine pi ct over sigma 1. Okay. So then this momentum vector or I'll write it as T sigma, okay, is T0 over C, and it's partial of X, partial T. So in other words, I'm using this formula here, and because I've chosen such a simple parameterization, this whole thing simplifies a lot, and this turns out to be T0 over C cosine pi sigma over sigma 1 minus sine pi ct over sigma 1 cosine pi ct, whoops, over sigma 1. And so now this integral, which is the angular momentum, turns out to be sigma 1 over pi T0 over C, integral 0 to sigma 1, and it's cosine squared of pi sigma over sigma 1 d sigma. And that's an integral that we all can do because the average value of cosine is a half. And so what we get is sigma 1 squared T0 over 2 pi c. Okay, well this is nice because this says that the angular momentum is proportional to the square of the energy, which is something that I remember when something that's true for what are called well, the slang term is Regge poles, which is kind of anyway, if you plot the angular momentum and the energy of various baryon or meson resonances, they actually follow a curve like that. And the curve then is the J, the angular momentum, or in this case, it's the intrinsic angular momentum, the spin of the hadron, is the energy of the hadron squared divided by 2 pi and then some constant T0C. And this is in fact observed by many baryon resonances. And these plots are called Regge trajectories. T0 is actually, I did a plot of a number of the baryon resonances, and I found that T0 was a 0.92 GeV per fermi. So this is a very, very strong tension. And the plot, since well, you can see the plot in the book. I'll just give you a graph of it. 0.8, 2.8, this is the energy E, and J over here goes as E squared, and so it looks like that. And the points on it are pretty good. This is the nucleon. This is I'll just write it this way. Delta occurs here. This is the 1232 resonance. Then there's an N star, 1680. An excited delta, 1590. Another N, 2200. And then a delta, 2420. They're all on this curve, and the errors are remarkably small. So in some sense, the baryon resonances of the neutron-proton baryon doublet is these resonances fall along what's called a Regge trajectory. Regge being an Italian theorist. And there are many other cases where this is true, and then there are some cases where it doesn't seem to work. but there's clearly a certain amount of truth to it, and so in some sense, when these hadrons spin, the action that describes their dynamics is that of a relativistic string, and you can imagine then that if you see the nucleon has intrinsic spin 1/2, this has intrinsic spin 3/2, and so whatever it is, it's essentially in some sense it's a relativistic string, and so in some sense it's described by this Nambu-Goto action. I think the Nambu-Goto action is probably unnecessarily elaborate for describing Regge trajectories. You could just say, well, you've got a relativistic, I mean, you could just say that the energy was proportional to the length of the hadron, and the angular momentum was given by that, and I think just relativistic kinematics could give you something like this. But it says that there's something true about string theory. There's something that hadrons to some extent are like, hadron resonances are like spinning objects, and they're spinning very fast, and what's holding them together is a very strong string tension. Now, originally people thought, well, this is how we have to explain the strong interactions. But then Gell-Mann proposed QCD and quarks, and at the same time, God, this guy whose name I forget, also proposed quarks. And then quarks were discovered a few years later at SLAC, where they had an electron accelerator, so they knew what the initial state was. They could analyze what the hell the final state was. And they saw that some of the electrons were scattered back. I think the first experiments were just fixed target experiments, electrons at 4 GeV going at protons. And some of the electrons came back. And it was like the Rutherford experiment all over again, so that there were quarks. Well, once QCD became popular, then it was thought that we didn't need this string picture of hadrons. And so people sort of lost interest in string theory for a while. And then in 1974, Joel Shirk and John Schwartz proposed that string theory be totally reinterpreted as a theory of gravity, and whatever else fell out. And unfortunately, when you take that interpretation, what falls out is so much stuff that we have no way, or the string theorists, I should say, have no way of figuring out what it means. Shirk, by the way, had diabetes and for some reason died at the age of 33 in 1979. So, okay. Well, I guess we can stop now. Are there any questions?
So at first I thought strings would describe the hadrons. One string was a hadron there.
Yeah.
Yeah. Okay.
That was the original picture, and there's some truth to it because that's a pretty good picture. And in fact, it's better agreement with experiment than anything else in string theory.
Yeah.
In other words, the modern view that it's a theory of gravity has zero contact with the experiment.
Okay.
On the other hand, supersymmetry also has essentially zero contact with the experiment.
And this view has basically gone away for now.
Yeah, it has, and but the fact is that nobody has produced a clear derivation of quark or let alone gluon in the QCD picture. And so I don't know. I mean, it's this confined. I mean, the lattice people, in my view, they build in confinement into the thing from day one, because when they use the same formalism for quantum electrodynamics of strong coupling, which is where they see confinement here, they also see confinement in electrodynamics. and obviously electrons aren't confined. So, I've always been skeptical of the confinement aspect. On the other hand, lattice QCD does seem to get pretty decent results for hadrons. But of course, as always, when you write a Fortran program, you have all this input data, right?
Yeah.
And you can, you can coax it along, and
Right.
it's not quite on a leash, but it listens to it.
Yeah.
All right, I guess we.
Well, sorry,
another question?
Yeah, just, so we went to, our angular momentum, there's only this 1, 2.
Yeah, the idea is that the hadron is spinning this way, going the angular momentum perpendicular.
So we've dropped all the mu's and just gone to 2 mu's.
Yeah. Mu is 3 values for mu: 0, x, y.
Okay.
T, x, y.
Okay.
All right.